Hi, this is Dibyendu Das, and today I'll be speaking about machine learning based hardware cost model for high level MLIR. This work was done along with my colleague Sandhya Manorswamy, and both of us are from Intel. So let's dive directly into the problem that we are going to talk about today. So if you look at the problem statement, let me just move this up a bit. Yeah, so look at the problem statement. What you're trying to do is to predict machine or hardware characteristics from a very high level description of a data flow graph. And what does that kind of a data flow graph look like is, you have, usually in our deep learning or machine learning workloads, we have these data flow graphs consisting of very high level operators. And let's say this is a kind of data flow graph that we are going to tackle. And we want to really see what this data flow graph's hardware characteristics will be if it actually runs on a certain kind of hardware, like what's its runtime, what's its throughput, registry usage characteristics, other hardware characteristics, etc. So the way we represent these data flow graphs today in many of these deep learning operations, especially with the advent of MLIR, is we represent it by a function. And the function takes certain arguments, which we show as, arg 0, 1, 2, 3, 4, etc. And they are of certain tensor types. And when we say tensors, these are nothing else but higher dimensional matrices with certain data types like F32 or B float 16 or things like that. And the dimensions of these tensors are given by, you can see this cross values. So if you see 6640 cross 30522, it just means it's a two-dimensional tensor, which takes in a data type of size F32. And then these are the arguments. And finally, what is returned by this function is another tensor of the similar size, but with the type being BF16 and not F32 anymore. And these are the operations that you can see from the left-hand side, which translates onto the right. We have a broadcast, we have a div, we have a cast, which is nothing else but moving from the F32 type to BF16 or similar, and then we have an add operation. So basically, this is the data flow graph, and this is the representation of the data flow graph in MLR, what we call as a high-level MLR form. Now, MLR can have different forms. You know that it can have dialects, which can go successively lower and lower down from, let's say, lineage, fine to SCF and things like that. But here it's like a very high-level, high-level dialect. Okay. To continue with the problem statement, this dialect that we're talking about, which we call as the XPU dialect, here XPU stands for nothing else but, it can be a CPU, GPU, an FPGA, any other hardware accelerator. So these are proprietary dialect. As I said, it's very similar to a very high-level dialect, let's say like MHLO or TOSA, if you're already familiar with some of those dialects. And what we want to do is we want to take this MLIR representation, and from that representation, without actually running it through our compiler system, through our code gens, through our optimizers, we want to predict certain hardware characteristics, right? So it can be, for our particular problem today, we'll just discuss about two hardware characteristics, mainly register pressure and what we call as XPU utilization, which is nothing else but, let's say, utilization of your vector units, utilization of your ALU, and things like that. And though this is currently being handled only for two, we can extend this, hardware characteristics to various other things, like you want to know about the total runtime of this particular piece of code, or you want to know the throughput, you want to know other characteristics like memory usage and things like that. You can use very, very similar mechanism to go and do that, what I'm going to explain now in the next few slides. So this is a very high-level problem statement. And from that problem statement, let's say, we want to motivate you guys as to why this problem is really important. Many of you know that in LLVM itself, we have been using the TTI and similar mechanisms to do things like, you are in the V plan or the vectorization plan unit, and you want to say, like, do I get any advantage by vectorization or not? And you usually will use TDI, or let's say unrolling and things like that. You usually would try to use TDI to gain some insight into what finally will be your your hardware runtime and other characteristics. So for the ML or the DL pipeline, many of these cases we want to do similar things at a much higher level. For example, we are trying to do fusion, which is a very important optimizations in deep learning or machine learning compiler frameworks. And one of these problems of fusion is, do you fuse a certain number of clusters versus some other? For example, do I clusterize this entire set of operations, or do I take a subset of it? And the reason for that can be many. So depending on your hardware characteristics, you may be running out of registers, you may be creating spills, register pressure, you may have memory issues and whatnot. So I may want to evaluate some hardware characteristics of this cluster on the left-hand side versus the cluster on the right-hand side. So that's one motivation. The other motivation is you may try to see the effect of one optimization on a cluster versus another. For example, for the same cluster, I may want to see whether a software pipelining works good or not. Now, for that, I really cannot run it till the end and actually do it when you are generating code for some of these deep learning machine learning systems. So you have to have a mechanism, let's say call a surrogate mechanism, by which you can do this kind of predictions and do evaluations. Even in cases like, for example, in TVMs, auto TVM, where we are looking at a large set of options to choose from while you are trying to generate code, we require some good mechanism to figure out whether an option X is better than option Y. So this is exactly what it tries to do. This particular problem that you are trying to solve is trying usually to compare between option X and option Y at a very high level of a data flow graph, which is represented by this MLIR opcodes, right? And in general, what happens, as you know, that once you get the cluster, which is this high-level MLIR code, you'll use some form of optimizing compiler. Usually we'll have what is called as the MLIR opt, which is the equivalent of LLVM opt. We'll lower it down to LLVM. And then depending on your hardware target, you may go through your CPU LLVM code, then to run it, let's say, on an Intel Xeon versus a GPU LLVM code, which will run on Intel Arc versus an FPGA, which will run on Intel Adjective, right? So these are the various options that you may have. But as I said earlier, we really don't have the time to really go and run all these various options actually on the hardware when you are evaluating X versus Y, right? So we want to do a surrogate mechanism by which we will get a fair idea of what the hardware characteristics would have been if we have run on a system A versus system B versus systems. So for us, what does the overall machine learning driven architecture look like for this kind of function, as I said, on the left-hand side, which consists of machine learning ops, which represents a data flow graph at a high level. So usually what we do is for training, as I said, we ingest data flow graphs, which are in high-level MLIR, which are what we call as tokenized. I'll just explain in a few slides what is tokenization. And these tokenized inputs are fed to a NLP-like neural network. Why it is NLP-like also I'll explain in a few slides. You can do various kinds of neural nets, but for this particular study, we have taken a kind of an NLP-like approach because we think that in the long run that may be easier to operate on kind of ML syntax and semantics. And during training, the actual ground truth, right? While you are going to do at the inference time or at actual runtime, you really cannot run them. But at training time, we actually run them on the real hardware to get what are the ground truth or the observed characteristics. And what are these? It can be your register pressure, it can be your XP utilization, it can be total runtime, it can be throughput, it can be various other things, right? And this phase of training, we have this neural net, we get this ground truth, and then we do back propagation to make sure that this particular neural net will kind of converge to a good value with a pretty high accuracy and low error count. So once that happens, we can consider the neural net to be well built or well representative of the training set that we have, and we can deploy it then for the actual scenarios while we are compiling or running the MLIR code at a high level. What does our training data set consist of? So what we actually do is we capture a lot of these data flow graphs, which are represented at MLIR level functions from our high-level frameworks. It can be frameworks from TensorFlow, it can be frameworks from PyTorch, can be other frameworks, but we get these graphs which are in MLIR level, and which is basically, as I showed you, is a sequence of xpu.ops and some input and output tensor shapes, and and the characteristics of that particular set of data. And so what we do is, for the data flow graph, we create a CSV file, and the CSV file is ingested as part of the training data set, consisting of the file name, which is just for our record purpose. It has the full MLIR text sequence. Now, how we encode that, we are going to show it now. There are the input-output tensor shapes, and also we will finally get the XP utilization or register pressure, which are the target variables which we are trying to predict. So these are, as I said from the earlier slide, these are actually collected by running them on the actual hardware or the simulator or things like that. Now, two kinds of CSVs are created for this particular work that we are presenting it to you today. One is only the opcodes are used as a sequence, right? So if you have the XP opcodes like the add, broadcast, cast, subtract, multiply, div, these are the only opcodes, and only the opcodes are used for representing your MLIR as well as the tensor shapes. The other case is when you have the opcodes as well as the operands as a sequence, so which actually will try to also kind of encapsulate your data dependence, like your use and def or the def use kind of chains in your MLIR data flow graph. Currently, we are still very early in our experimentation and things like that. So usually, for your ML training and all, we require a huge number of training samples for a data set. Currently, we have about 20K plus, which I think is reasonable for the timing, but definitely, as you go and do more experiments and collect more, we expect this to go in 100,000 case kind of stuff. And then we expect our training accuracy and error to be much better when that arises. Now, as I told you earlier, the crucial piece of this work is how do we represent this MLIR input code as a form of a sequence so that we can do proper models for that. And as I said, we are going to take the tack that we are representing these as kind of NLP problems. So what we want to do is we want to represent this whole code as a kind of a text sequence, and that from that text sequence we want to predict our numbers, whatever those are. Okay. So these are the various pieces that we collect as for that. One is the input tensor shapes. As you can see, these are the tensor shapes, right? Here it's a three-dimensional tensor of type BF16. Now, for the time being, I'll really may have time to explain to you. Currently, the entire tensor shape is taken as one single token, which means that we are not breaking the tensor shape into individual numbers. One of the reasons being, what we see in deep learning and machine learning is many of these tensor shapes are very kind of popular shapes and they appear again and again. And the other reason is we want to keep our sequences smaller. If you break it down, the sequences become larger and sometimes they may have problems in creating the model. But that's not really a very big issue. You can break it down and do your experiments later if you want. So you see the output tensor shapes, input tensor shapes, you see the output tensor shapes. And what is the opcode sequence representation? So here, as you can see, we will represent this opcode sequence like this. We drop all this XPU syntax. We also drop the tensors here. In this cases, this tensor just means what is the size of the output for this. We just drop these at this point of time kind of assuming that many of these are kind of represented by the input and the output arguments. Once again, we can also encode this particular tensors as a sequence along with this sequence and have kind of two parallel models running and kind of joining at some point. That's also possible. But let's come back to what we did. So what we did is we simplified this sequence by taking out the XPUs and these tensors. And you can see this is the sequence. You have some hashes, double hashes in between to kind of, differentiate between each opcode, right? This is the percentage, this is the percentage one, and so on. And finally, what we do is for the first problem that we solved, we kind of ignored the operands and we just took the operators, right? So the sequence here right now for this particular MLIR will just be 3 adds, right? Because there are 3 adds. And these are the input tensors. These are the 4 input tensors. And this is the output tensor. So this is, you can see, is an 8 input sequence for your MLR in this particular example. And so one of the main things that you do when you do this kind of NLP-like solution is you have to encode these tokens. So this encoding is nothing else but giving a number, a numerical value to this text tokens so that they are unique. So for example, if you look at this, which is a longer sequence here with sub, broadcast, mult, add, and this, you can see that both the subs gets a token value of 13, while broadcast gets 4, and so on. And you see that this particular tensor size of 3 cross 3 cross 64 cross 64 cross F32, it gets a token of it gets a token number of 112, while 1 cross F32 gets a token number of 5. And you can see this getting repeated because these sizes are getting repeated. So this is what is called as tokenization. Now, in general, for people who are familiar with some of the modeling for machine learning knows that this kind of encoding creates a very sparse vector representation, which may not be good for your models or training. So what we need to do once we do this encoding is it should be followed by something called an embedding, okay, which creates a dense vector representation and also good for your learning. And this embedding currently can be done as a pre-training, right? We've seen like transformer or BERT where you do a pre-training and do an encoding. Or you can do encoding while you are doing training. And that's what, embedding while you are doing training. And that's what we are going to do here. We have done embedding as part of the training. And so these are the models that we have looked at. And finally, one of the models which have performed best, the figure is shown here. The 3 models we tried were a simple sequence of fully connected layers, right? So what we did was, if you look at the previous diagram, or let's say the one previous to it, you take the sequence, right? And you have some maximum sequence number and feed it through a simple MLP or a sequence of fully connected layers. Okay, so this converged in general with a fair amount of accuracy, but not as good as we wanted it to be. We also passed the same sequence through LSTM, which is a very well-known model used for text sequences and things like that, which performs better than FC, but still not there is some accuracy or drops and things like that. One which we saw perform best. Now, once again, if you do your own experiments, it can turn out to be slightly different. But from our experience, what we saw was when we apply a con boundary with a max pool followed by FC layers, that's what performs the best today. Sorry, in terms of root mean square errors and best in terms of accuracy. So what we do here is, this is a model. We have the MLIR code. We do the tokenization and encoding, and then we do, as part of the training, we do the embedding, right? We pass it to a con boundary, we pass it through a max pool, and we pass it through the dense layers, and then we have the predicted hardware characteristic. Now, in general, also you can pass auxiliary hardware inputs, which means that you can pass additional information about your specific hardware. Let's say CPU or GPU or FPGA or hardware accelerator. We haven't done this in our work, and it's optional, but you can do that. So this is the main model that we have finally tried, which gives fair amount of accuracy and a low amount of error. for the MLIR code that we have looked at. And so these are slight details about that model. So it's a con1D plus max pool per FC. So I cannot show you the code here, but it has 6 con1D layers for people who are familiar. So with filter sizes of 2, and we have a single max pool 1D followed by 3 FC layers. And this is mainly for both predicting register pressure as well as XP utilization. So you can see that from the old sequence, once again, we have these 3 adds followed by our tensor sizes. And what we do is we take this con1D and kind of move these, move these filters and the con1D layers across our sequence, followed by our max pool, finally predict our reg pressure or XP utilization. And we see that we get fairly good results. We see a root square error of only about plus minus 5% with respect to register usage. And we see a root mean square error of plus minus 4% when you are talking about XP utilization. Now, this is only done for certain systems. It's not that we have played around with a lot of other systems, but these are very initial results, which looks very promising. And these are examples of some predictions. For example, what we see is for register pressure, the amount of the number of cases or percentage of cases where the difference is 0, which is like no difference with the actual versus prediction, is close to about 20 to 23%. Where there is a difference of 1 register prediction difference, it's about 50%, and so on and so forth. And the number of cases or the percentage where you have greater than difference of 3 registers is very low. It's like close to about 6 or 7%, which means that you're doing a fairly good job, let's say, with respect to register pressure prediction, when you are using this kind of a system with MLR at a high level and using this NLP kind of model, right? The other, which I'll go very quickly because I'm kind of over time, that we also use the mapping of the both operators as well as the operands, just not the operators. So we use the same sequence, but also tokenize our operands that we have. And these sequences are longer, obviously, because you are now tokenizing also the operators and the operands. On an average, we see are 4x longer, and so the training is slower. And we may have some out of what they call as out of vocabulary problem with respect to this, which we'll not discuss here. But in general, we get better accuracy. Now you see that the cases where we have 0 difference is almost like close to 75%, while the others drop substantially. So as you can see that if you go from a simple operator-based modeling versus an operator and operand-based modeling, you get much better accuracy. So yeah, I come to the end of my talk, and the next steps are like we need to run with larger training sets. 20K may not be big enough. We need to use probably other models like transformers to see how they are doing. We need to also integrate in a production compiler. This is like sitting outside a production compiler for the time being. And then there are open questions like, should you do pre-training? And then can we extend similar prediction models for other MLR dialects like Affine or Lineage or SCF and things like that? And these are a few of the references. These are pretty well-known work. Learn performance model for TPUs at MLSys. One of the good works from which I've taken a lot of ideas are the end-to-end deep learning optimization heuristics by Chris Cummins et al., and also from Ithamal, which is Charit Mendes' work published in ICML 2019. So with that, this is the end of my talk, and thanks a lot for providing me this opportunity to present to you my and my colleagues' work at this well-known forum. Once again, thank you all, and I'm open to taking some questions. Thanks.
Okay, perfect. So Zoom is working. Dibyendu, you can hear us, but you're muted.
Yeah, I can hear you.
Great. First question.
Good morning, and thank you for a very interesting talk. It seems that it can have very broad applications. I wanted to ask about how does the model behaves when there are function calls? Because the way you're tokenizing it, I guess you are I don't know, if you're throwing out the information about which function is called, can the model somehow recover that information, and or do you do inlining before you're running through the training and through the inference or not?
Okay, good question. So at this point, we are at a very high level MLR for usually TensorFlow or PyTorch kind of inputs, where in general right now we are not having other called functions from this particular function. But in future when we are talking about them, what we need to do is for those called functions, maybe we require some kind of pre-training definitely to understand some of the logistics there, especially also if there are other library calls and things like that. But also as you said, we can if you are inlining everything, that's fine. That probably you can still use the current methodology. But I think we need to take care of either intrinsic calls or special library calls or even user-defined calls in a slightly different manner. By I personally think we should do some amount of pre-training.
All right, thank you.
Have you tried using graph neural networks for this instead of the NLP approach?
Yeah, that's a good question. The thing is, we didn't, mainly because of the fact that there was some feedback from some of the people who have implemented GNN that with longer sequences, we may run into scalability issues with GNN. Though currently our sequences are not really very long, sometimes it may run up to several hundreds to maybe close to 1,000 sometimes, because these are usually text sequences. So we didn't try that, and principally because of that, because from MLIR, our plan also is to move towards lineage or affine or SCF, where the sequences will be much longer than what we have here. But definitely, I know there is a panel coming up later in the day called MLGO, where some authors, some of the panelists are going to speak about that, and there are already some work on GNNs with this kind of thing. So definitely it will be good to see whether GNN can provide good comparative or even better prediction accuracy compared to the NLP-like approach.
Thank you.
Thank you for the talk, first of all. Can you tell more about how you plan to use predictions to drive the optimizations or plans? What you have?
So one part of that, we probably touched upon very briefly. One of them may be a very important optimization, let's say called clustering, called fusion, which we do in the deep learning, usually in the deep learning frameworks, compiler frameworks. So what happens? Let's say you have to choose between a cluster of 5 nodes or a fusion of 5 nodes versus a fusion of 7 nodes. And sometimes it may so happen that the fusion of 5 nodes may actually be better than the fusion of 7 nodes due to various, like maybe you are going to run out of your registers and going to go a spill, and then actually that causes more memory traffic and performance bottleneck for you compared to the smaller one, which is not intuitive. So that's one. The other one, which we are planning to also look at, is when you are, in the pipeline. Let's say you are part of the MLIR opt phase, and I want to do a loop interchange. And so I want to do loop interchange, but I really don't know, and I really don't want to explore all sequences, but maybe a restricted amount of sequence. So what I can do is I can take each of these few sequences, and I then can predict the runtime for these sequences using this kind of a mechanism, rather than going like, what happens in TVM or something is like you go and probably try to run through and at least generate the assembly or at least do some kind of simulation to get an actual number. So we are currently visualizing this 2 or 3 different scenarios.
Thank you.
So in regards to benchmarking XP utilization, have you seen any problems with repeatability between those benchmarks, and how are you dealing with that if you are?
So come again regarding the XP utilization. Can you repeat the question, please?
Sorry. Oh, so if you're if you're benchmarking basic blocks, like you'll have to find steady state, and you can have some problems with like repeatability between benchmarks. So you're seeing issues with that with XP utilization?
So the thing is, the only utilization we have studied right now is the occupancy of our vector units. So we haven't done any generic other utilization at this point. So because we're just looking at the occupancy of our vector units, mainly if the vector unit is full or empty or things like that, because of how the scheduling has happened or how the register allocation has happened. So in general, we haven't seen much of a problem, but yeah, maybe, once we look at more complex stuff, maybe we need to look at something. But yeah, no, we haven't really got deep into that.
Okay, thank you.
Okay, so that was our session. We're going to have a 30-minute break, and there's coffee and tea. I'll see you after. Thanks to speaker again.